Okay, uh, welcome everyone. Appreciate you joining us today for day 3 of the high performance seismology cyber training. We're going to start a session now on ground motion simulation and analysis tools. I'm Phil Mackling. I'm SCEC software staff. And we'll have a presentation, and Fabio Silva, another member of our SCEC software group, will present the GMSV toolkit in detail. I'm going to give a brief introduction to SCEC ground motion validation or ground motion research before as an introduction to the ground motion toolkit. So sorry, let me make sure I've got the right presentation. Okay. All right. Well, thanks again for joining. We're going to get started here. I'm Phil Macklin. I'd like to give a brief introduction to SCEC's ground motion simulation research. The GMSV toolkit is kind of the latest development in this area, but it's a kind of a broad activity with a wide range of capabilities that have been developed here at SCEC that I'd like to touch on. So I think the kind of the starting point is that SCEC is working on what we call a earthquake system science approach. So we're really trying to integrate information from a wide range of domains and wide number of fields to better understand and characterize seismic hazards in California. So this is slide kind of suggestive of the kind of the large number of different data sets, observations, models that in some sense need to be taken into consideration to really understand seismic hazards. So not only is there a lot of kind of fields that need to be considered, but it's we're developing predictive models, and there needs to be an iterative process where we develop models, add new physics into them, but then to test them in some rigorous way to confirm that they do produce or they do match the behavior of the real world. So this is this iterative process, develop the model, run some simulations, verify and validate that the model performs well, and then continue again for another improvement cycle. So specifically, activities that support this, I'm going to mention a number of them here. So one is that SCEC develops earth structure models and we've been focused particularly on models for Southern California. So significantly, two significant ones are California's seismic velocity models and fault models. There are others, as I mentioned previously, but session 3 today will give an overview, and we'll talk more about the models that exist and how you can access the information that they have. But this is an example of a velocity model. It defines typically the VP, VS, and density for each point in a predefined region. They can vary in their extent. In some cases, they'll go down to even 100 kilometers, but top 50 kilometers in some cases as well, or So then fault models, description of where are all the active faults in California. And active, it means, is meant in this group by evidence that they've moved in the past 10,000 years. Another important component are rupture models. So how the slip time history, how the faults rupture over time, how the waves propagate down the fault structure. There's a couple of different versions, kinematic models that predefine the slip and rupture speed, dynamic models that simulate friction properties. This is a kind of comparison of those two, the behaviors that you get out of either, with the dynamic being more physics-based, but significantly more computationally expensive to generate. Then there's, once you've got region-specific structures and ruptures, now you need models that generate, propagate the waves through solid earth. And there are different methods within SCEC community that do earthquake wave propagation. Some cases they propagate through 1D velocity structures, other cases through 3D. The computational requirements go up dramatically as you go from 1D to 3D methods, and as the maximum simulated frequencies are increased. The broadband platform, which we'll talk about here in a moment, it compares multiple methods, simulation methods, propagates waves through 1D velocity structures. It's been used for engineering purposes, and it's open source software that can be installed and run on your own servers. What I want to express is one of the key ideas is that the broadband platform supports multiple models. So there's different methods for propagating waves, and the toolkit allows you to select kind of the collection of components and test the behavior of different alternatives to see how well they compare. The 3D wave propagation are often, there's exercises where they compare the results from alternative methods. So SCEC supported finite difference codes from Rob Graves, finite element code, CMU Hercules, AWP ODC code from San Diego State University. And then we've performed comparison exercises for the wave propagation codes, run the same problem, and evaluate whether they produce equivalent results. And the codes now actually behave quite similarly. This is an example of something we call a cybershake map, but what I want to communicate is, in some sense, the difference between 1D models and 3D models. If 1D model, the earth structure is all the same, and basically we would expect, and they in some sense predict or model, that the strong shaking is right next to the fault. But when you have a 3D model that identifies where basins are, often the 3D methods indicate that strong shaking will get trapped in those 3D structures. And so even though the ruptures are the same, the expected ground motions produced by the different methods can be quite different. So this work has led to a collection of open source software tools that we call the SCEC software ecosystem. I won't go through all of them, but this is kind of a collection: fault models and earthquake rupture forecast, broadband platform, wave propagation codes. Here are some publications, important publications that have been produced using these different codes. So we're moving toward And the main topic today is the ground motion simulation validation work. And I want to connect that into some sense lesson learned. We've been working on this for almost 20 years. And we've kind of recognized that the amount of verification and validation that's required for simulations, in some sense, it depends on the end users. If the end user are just individual researchers, you can be quite experimental and just introduce new kind of innovative ideas. But as you move up, and now if it's a collaborative research project, then there more structure and evaluation is required. Maybe version code, associated tests. If you're giving the results to engineering groups, now what the level of testing with probably will require community-defined validation problems showing the results that you get. And if you're giving information to public and government, you have quite stringent requirement for the evaluations that you need to be done. The GMSV is in some sense set up to support these higher levels of forecast evaluations. So this is some examples of the type of forecasts and testing that we do on different types of earthquake, seismic hazard information. But the one specifically we're addressing today is the ground motion simulation validation activity. So this is a collaboration within SCEC that includes geoscientists, but also civil engineers. The civil engineers are identified as end user of our result, and they help identify, here's how they want the results, our ground motion simulation results, to be evaluated. And so we're basically learning from the civil engineers what type of evaluation, verification, validation tests to implement. And that's been an activity of this GMSV committee. But if you go through this process, it helps you have a significant impact. So some of the SCEC work has been influential in the city of LA resilient by design plans. So Fabio now is going to present the GMSV toolkit, including a software tutorial. And the goal is the toolkit is specifically designed to develop quantifiable and technically defensible assessments of simulated ground motions for use in engineering applications. So again, my emphasis is the way seismologists evaluate simulated ground motions differs than the way engineers evaluate simulated ground motions. And this GMSV is really targeted to support and distribute and give access to the way the engineers want to evaluate our simulated ground motions. So I think that's where I'll stop. And Fabio, I'll stop sharing, and maybe this is a place where you can start.
Thank you, Phil. Let's see. Share my screen here. If you guys can see it, just get this going.
Yes, looks, you can see it.
It's great. Okay. There we go. Okay. So good morning, everybody. I'm Fabio Silva. I'm a computer scientist at SCEC. And today I'll be talking about a new open source software package we've been working at SCEC, which is the GMSV toolkit. So I would like to thank Phil for his introduction, and also for Scott Callahan, who will be supporting us with any technical issues that we have during the tutorial on the Slack channel. So the plan for today is to start with the GMSV toolkit. I'll give you an overview of what it is, where it comes from. I'll spend some time talking about the current components that we have in the GMSV toolkit. and try to give you some examples of how it can be used for the validation of simulated ground motions. As I'm going to talk about in the next few slides, the GMSV toolkit comes in great part from the broadband platform. So I'll spend then a few slides talking about the broadband platform, introducing to folks that haven't used it or haven't heard of it. And also I'll give you a status update for the latest developments on the broadband platform we had released last year. And then we'll shift to Jupyter Notebook, where I hope to give you a few examples of how the GMSV toolkit software package can be used to process time series, calculate metrics, statistics, and finally generating some plots. And then, I'll touch at the end with some description of the status and time frame that we have for the GMSV toolkit release. As I said, this is a new software package that we started last year. All right. So let's talk about the GMSV toolkit, which is the SCEC ground motion simulation validation software toolkit. So this came about maybe in the 2022 funding cycle as a SCEC proposal, mainly from Christine Goulet, Phil Macklin, and myself. And the main goal is to make a set of existing codes, mostly from the broadband platform, but also from the TS process cycle running package, which is, comes from another project that we have, the HIF project. So making those codes available as a standalone codes that could be used independently of other pieces of code. So as we'll see in a few minutes, the broadband platform includes a collection of metrics calculations, statistics, plotting codes, and they can be used for the ground motion simulation validation. But those codes have been used for, I don't know, I've been on this project for 12 years now, so they've been used for more than a decade by SCEC scientists, engineers, and many others outside of SCEC. And it is a result, as Phil mentioned, of collaboration of a great many SCEC contributors across different projects at SCEC. Now, using these codes is the top, or I would say maybe it's the second top request I get in this 12 years working on the broadband platform. I guess the main question I get from people on the broadband platform is, can I use broadband in this region that we don't have a velocity model? So that's the top question. But the second top question is, can I use these metric computations outside of the platform? How do I access these codes? And codes that are part of the broadband platform. And those were, those codes were initially created inside the broadband platform and include many dependencies that make it really difficult or perhaps impractical for those to be used separately. Now, with the GMSV toolkit, we aim to decouple those codes from the platform and also those from the TS process. And removing dependencies, we have, removing hard-coded paths, file names, assumptions, basically making those available as in a standalone form. So how do we go from, from goals into actions? As I mentioned, we wanted to migrate a number of existing codes from broadband and from TS process, remove things that make them dependent, and also separate, them individual pieces so they could be easier to script those in different ways, the way, other users would envision using those. So one of the main things we talked about on the broadband platform is be able to generate reproducible results. And we wanted to be able to replicate that in the GMSV toolkit. So for that purpose, we include an extensive number of tests to make sure that the tools still work. And also we got a continuous integration set up on GitHub to automate some of this testing. So, it runs after every commit. So that's been working. And I think so far we have 40-some tests there with more to come. So I prefer to do those as I go along, as opposed to just add the test at the end. I find that helps me during the development. We also wanted to make these tools accessible both with a command line interface and through a Python interface. So, you can use them either on the shell, you can script them, or you can use directly from other Python codes. Last but not least, I guess, the documentation plan, was included in the proposal to make sure that GMSV toolkit includes a complete set of, command line documentation and a Python API documentation, various examples, sample workflows of how to use those, documentation about the file formats, what goes in, what comes out, basically, I think we see documentation is a key to this project. Okay, so we started this work last year, and we had, two separate repos. We had broadband, and we had TS process. So we created a new repo, moving lots of codes, removing dependencies, preserving, trying to preserve other functionality. In fact, when we are done, I guess I'm hoping that within the broadband platform, we can just source codes directly from that repo, so we avoid duplicating, codes and making, code maintenance a little easier. Already, some of these codes are already used across multiple SCEC projects. Like I know Broadband and CyberShake share some of these codes already. So it'll be great to have a single place that we share all of this. Okay, now from our proposal, here's sort of like a list or what we included there. So from the TS process package, we have a number of seismogram time series processing codes, things like rotating, filtering, alignment, resampling, baseline correction, converting across different formats. So those all come from the TS process. And from the broadband platform, there are several codes doing computational validation metrics. We have errors intensity, duration, RODI 50, the FAS, metrics from the RZZ 2015 paper, directionality metrics, in ground motion model computations. And so those are all included in broadband, and they have been validated and used for a while. So broadband also includes a number of other statistics, computation codes, goodness of fit plots, seismogram comparison tools, that's all that stuff. So we kind of decided to start with those. And I'm going to give you an example now. So this is one way these codes can be put together, I guess. This is the diagram of the PSA validation. PSA is a pseudospectral acceleration validation on the broadband platform. So in this case, we start with simulated and observed time series. They go through this RODI XX code where we compute RODI 50. And that's done station by station. And once we have those, we can generate per station comparisons of those. We can also, use earthquake description, which describes the rupture, which we're going to cover a little later, and a list of stations to calculate, ground motion models. So, for example, how does that compare to, the NGA West 2 models? The broadband can do that, and those can be compared to each other. So we can compare simulations against observations, ground motion models against observations to see how they perform. I can compare two different sets of simulations. Any of those two can be compared and a goodness of fit plot can be constructed, basically showing how these two data sets compare across, a range of stations. So again, before, everything was done inside the broadband platform, but it was not truly accessible from the outside. And here's a similar diagram. This time, this is with the FAS workflow. It sort of follows the same steps that we just saw before. And I say this is something a little new. This appeared in the last release of the broadband platform. We just came just before the SCEC meeting last year. We added FAS, the broadband, to complement the PSA analysis. And I think PSA, as I heard from Christine, PSA is the main metric using building codes. That's why it was used initially on the broadband platform. As Christine describes to me, is a simple metric that mimics the structural response of buildings and bridges and other structures. But with FAS, we can perhaps understand better the physics, any issues with data that we don't fully capture with PSA. So, together, these two, I guess, provide a better seismological interpretation of those results. And here are some of the data products from the PSA pipeline. So on the top left, we have comparisons showing PSA for 3 stations. And some of these we're going to see later in the Jupyter notebook too. So, this is just sort of like a brief introduction to those. At the bottom, we have a map goodness of fit plot showing how each of those stations matches the recorded data. And in this case, I think I'm using the 1994 Northridge earthquake for comparison. And on the right side, we have different goodness of fit plots showing how the simulated data set matches the recordings for Northridge. As I said, we're going to see some of these in more detail as we go into the notebook. Here, a similar set of plots, but this time using FAS. We produce per station FAS comparison plots shown, on the left side. On the right, we show how simulations and observations compare across all stations. This is basically the same idea that we have with a PSA goodness of fit plot, but this time applied to FAS. So these are all new data products that came with the latest release of the broadband platform. And the broadband platform includes a number of additional metrics and other data products that are perhaps not part of the standard workflow, but they're all being there. In this case, on the left-hand side, we have the 2004 Anderson goodness of fit plot, which sort of scores on a per station basis. You can also do an aggregate, combining all the results using 10 different metrics across different frequency bands. And these are examples of codes that have been available within the broadband platform, as additional metrics that have been implemented by the community. This particular two codes have been implemented by probably as part of a SCEC proposals, and they've been eventually integrated into the broadband platform. So I think I talked a lot about the broadband platform. So what is the broadband platform? I'm not sure all are familiar with the SCEC broadband platform, but I like to say that the broadband platform is basically a collection of open source scientific codes. It's a result of collaboration across multiple, several institutions and several groups. Right now we have 7 separate simulation methods built into the broadband platform that allow us to generate calculation of broadband seismograms at user specified locations. So I see, Scott, you have a question?
Yeah, there was a question in the chat. Felix, would you be willing to unmute and ask it directly to Fabio?
Thank you. It's very interesting. I come from the world of the waveform modeling, so for me, it's impossible to think about waveform modeling for high frequencies using a 1D velocity model. Still, I see on your graphics that you can produce high frequency PGA simulations with a 1D velocity model. In the previous talk, we already saw that using a 3D velocity model may include important differences. Still, I can perceive that 1D velocity model can still deliver for PGA at high frequencies. Is that true? Or what is the limit of 1D velocity model for this kind of studies?
So that's a good question. And, so as the broadband platform is always a trade between, how much computation you're willing to spend versus, how much what you want. So so the broadband platform, I don't know if Phil included that in his slides, but it includes a combination of simulation methods, right? So for example, in the Graves and Ptarka simulation method, we have the low frequency component, which is deterministic, and we have a stochastic component, which is the high frequency. So I think it goes up to 1 Hertz. You do the deterministic on the broadband platform using the 1D velocity model, and then you do the stochastic after that using the velocity model, using the rupture, we call the SRF file, which is a rupture description. I can show an example in a couple of slides, and those are merged and combined. So to create like a broadband velocity model. But I guess there are limitations of what we can do. I don't know if that maybe answers your question.
Yeah, thank you.
All right. So so I'll just keep going. Please feel free to ask questions, and Scott, you can bring those to me. Anyway, so we have this collection of codes on the broadband platform, and includes, as I just said, codes for rupture generation, low and high frequency seismogram synthesis. We have site response for adjusting the produced seismograms to site conditions, and we have a collection of post-processing and plots codes for visualization. So a couple of things that makes the broadband platform useful, I guess, in my opinion, is that it allows for the use of common input files for all these methods. So you have the same source description, the same stations, the same parameters that go into different methods, and it makes it easy to compare or easier to compare the output, if you're starting from the same inputs. Another thing I find it useful on the broadband platform is that it's a way to generate reproducible results. So you run the broadband platform with the same seeds, with the same parameters, and you get the same results. And this is important for engineers. So now what's new on the broadband platform? So the 22.4 release, which is the latest release that we got last year, adds this FAS validation pipeline to the existing PSA codes. We add support for multi-segment ruptures for most simulation methods. I guess here on the top right, we see a rupture model for the main 2019 Ridgecrest event. I mean, before a rupture on the broadband platform was like a rectangle. You could move the rectangle down, up, you can turn it a little bit, but it was still a rectangle. With the multi-segments, we can, bend them, we can have a set of rectangles that we can, put them in it's more flexible to represent this. And here we have Ridgecrest. I think we see the hypocenter on the second segment, and see, so this is the output, for example, of the rupture generator. It reads the source description, which is, the fault mechanism location, and produces this rupture model for the event. We also expanded regions in California, I guess maybe due to the addition of Ridgecrest, basically. So we have this new region, the Southern Sierra Nevada, or maybe the Southern Walker Lane region. So on broadband now, California has 5 regions. As Phil mentioned, on the broadband, we can do 2 types of simulations. We can do validation simulations or scenario simulations. So on validation simulations, we choose a historical event for which we have recorded data, and we use a simulation method to compute synthetic sine ground motions for each one of those stations. We use the historical event description to generate acceleration, velocity, seismograms for that event. And on the right, we have the station set that we use for like the Whittier Narrows earthquake. And then we compute against those stations, and we can calculate a comparison against the recorded data for an event that we already have. And this is useful for example, for calibrating methods. If you're developing a new method, you want to see how your method performs against recorded data, but also can be used to help analyze the data for new events. And this is a list of events that we have on the broadband platform. As you see, we got some new validation events added in 22.4, and some of the ones that we had before we added as a multi-segment, like landers. We had landers before, but it was always single plane. Now it's like a 3-plane event that implemented on the platform. The platform can also be used in scenario simulations. And these are different than validation runs because those are hypothetical. Those are what-if events. With user-specified locations for the stations, it doesn't have to match recorded data because those are hypothetical events. Since we don't have any recorded data, the broadband will create the ground motions. It will create PSA and FAS file for those, but there's no comparison, right? Because you don't have recorded data. Then the stations are up for the user to choose where to place those. On the right-hand side, there's an example. I just placed stations in a 0.01 grid. And then later on, right after Ridgecrest, we run the broadband platform on a grid here in California, going from, I guess, 35.5 to 37 degrees, and calculated, generated the intensity map on the right side using PGA. So that's an example of what the broadband you could do with that. So now I think I'm getting to a point where I'm going to switch to the Jupyter notebooks. Are there any questions? Slack or in the chat window? So
I don't see any, Fabio, so I think it's okay to go ahead.
All right. I'll just keep going then. So as described before the session began, there's you should have Docker installed. You should have the container downloaded. There's the Docker run command there to run this particular container. And once you do, you open the URL on a web browser. You're going to see this page here that has this is the only notebook that's there. Once you click in there, you should have a second tab opening. on your browser that should include this introduction to SCEC ground motion simulation validation to a notebook there. So I'm going to switch, Phil, I'm going to switch to the notebook. Let me just make sure I get the notebook ready. Okay, can you guys see my notebook?
Yes, I can see it. Okay.
Okay, so we're now okay, so I'm gonna, so hopefully, you know, you have your notebook open. If you're having issues there, you can contact Scott and Phil on Slack for help. And here's sort of like a brief summary of what's included in the notebook. I plan to walk you through this today, but feel free to also come back to the notebook and try other things. As we've said, this is the provides an interface to the GMSV toolkit that's installed inside the container. And there's plenty of text here. You know, it should hopefully be self-explanatory, hopefully. But you know, if you have comments and feedback, I always welcome those, and please send those to us. I'll give you a link at the end. So this diagram shows the workflow that we're going to follow today. So we're going to start with two sets of seismograms. We have calculated seismograms that came out of the broadband platform, and we have observed time series for the 1994 Northridge earthquake. So we're going to compute RODI 50 for each one of those sets, and we're going to create comparison plots for a station. We're going to pick a station and create comparison plots. Then we're going to aggregate data from all stations, across all stations, and generate different types of goodness of fit plots. At the end, we have a little exercise to try to generate comparison plots ourselves. So the first thing we're going to do, there's a box here that imports, Jupyter functions that lets us visualize results. So we're going to run those, and there's two ways. I mean, I think Phil mentioned that in the previous session there. You can click on this run button on the top, or shift return on your keyboard. That also, steps through that code box and moves you forward to the next one. Let's see. So just so we understand what we're doing, we have the input files that were used on the broadband platform to generate those seismograms that we're going to use today. On the right-hand side, I think Phil mentioned that we have a 1D velocity model for the whole LA basin, and this is what we have. That's the VPVS and density that was used. That gets you start with that. I mean, when we set up the broadband platform for a region, we start with that. Then we need to calculate Green's functions for that region, and they go up to a distance, and those are 1D Green's functions. And that's one part of the simulation, the validation. We also don't show here, but we have the comparison data for a number of stations. And then here we have the source description for Northridge that we use, and also a station list. So in the source description, we define magnitude. There's a rupture location here. There's and those are parameters that describe the Northridge rupture that was used for the simulation. And then we have a list of stations, and for each station we have longitude, latitude, a station ID. So in this case, that's the station ID. We have the VS30 for that, the site for that particular location, and we have this range of frequencies here. That's basically it's more informative, and we'll see that later on. But it basically tells you for that particular station, for the recorded data is good for that range. So that depends on what kind of equipment was used to record the time series there. So we're gonna scroll down a little bit. So this is an example output. So this is a BBP file. So this is a velocity file that comes out of the broadband platform for a station. This is the first few lines of that. Is a text file, has 4 columns. You have timestamp, 2 horizontal components. I guess we have north, south, and east, west in this case. And we have a vertical component, the up-down component. That's the last column. So this is what we start with, right? We're going to start with a collection of those files. But before we do that, there's two cells here that basically tell Python about the locations of all those files, station lists and source files and all that sort of stuff, input directories. So we're going to step through those two, make sure that we set up all these paths. And the first thing I like to do is, so we have the stations and we have the fault. Let's see what create a station map. So I'm going to import the plot map module from the plots package. And as you noticed before in the two text boxes that we clicked through, we actually have two station lists here. We have one, which is the full, 39 stations that we use for Northridge. And we have a second station list that I just chopped the first one and put the first 3 stations there. And we're going to use this shorter station list to speed up some of the tests, some of the processing here. But you can always use the longer one if you want, and we will switch towards the end. But this gives you an example. So we import the plot map module from the plots package, and below, we set up a title for our plot, and we set up the output file, and we run this plot map command. And this is for the all stations. This is the 39 stations. We repeat that here at the bottom for the 3 stations, just so we want to see both of them, see what we're dealing with. And then there's a cell here that probably show us plots. So here's what we have: the Northridge rupture and the 39 stations that were used for the simulation. And if you scroll down a little bit more, here we go. Those are the 3 stations that I picked. Since I picked the first 3, those are the closest to the rupture. I think the station list was ordered by distance, so I guess we'll have those. So they're pretty close there to the rupture. So I'm going to scroll down a little bit. And the next thing I would like to do is generate seismogram comparison plots. So we get our acceleration files, and we'd like to create, displacement and velocity files for those 3 stations. I guess we're using those 3 stations for this part. So we can use the GMSV tools module from the utilities package, and we're going to use the short station list. And the tool, as I click through here, so I'm going to import that. And then this is for the simulation. So as I run this, I guess for the velocity, it just copies over because there's nothing to do. But then it calculates velocity and displacement from that file. So we have a full set of files for that. We will repeat this for the observed data, right? Because I want to do the same thing for the recorded data. And again, it does the same thing, copies over the acceleration file and, generates velocity and displacement. Now that we have 2 sets of files, we're going to pick one station. And I think I picked the first one. Yeah, I picked the first station there. And this example, hopefully, I guess it's easy to follow, but we set up an array of files that we want to compare. We set up labels, we define the range we'd like to see, and we run this single station method. I'm going to do that. And we can see the result. Okay. So here's what we have. So we have simulations in black and observations in red. And the first thing you're going to see and tell me is that, those are not aligned. Right? So we see that right away. And this is expected. Then that's due to the fact that the observed data begins at triggering time whenever the instrument gets triggered, and the simulation starts at origin time, and then there's a delay for the wave propagation to happen. So just looking at this, I actually don't need the labels to tell me that the delayed one is the simulations. But if you had a station that was like 100 kilometers away, this will be shifted much to the right. That's expected. It can be changed. It can be aligned, right? But for this difference, this time difference or this time shift doesn't have an effect on the PSA workflow, doesn't affect the metric, but it can be addressed, by some of the seismogram processing tools that we have in the toolkit to basically align those. So these are the two seismograms that we have for that particular one station. And we're going to have seismograms like this for all, the 39 stations. I'm going to scroll down. And the next thing I would like to do is to calculate the PSA or the RODI 50 for those. And again, we have to do it twice, one for the calculated ones that came from the broadband platform and one for the observed data. So we first import the RODXX method from the metrics package. Let's see that. And then, as I said, we're going to run this 2 times. One time, I'm going to run for the simulated data, and then I do it once again for the observations. I guess we have plotting codes that tell us what we got. So we're going to import the plot DXX from the plots package. We set input folders for those files. I put labels. So in this case, I'm labeling, the observations as NR for Northridge. That's the recorded data. And I'm labeling, the simulated data with this big number. This big number came from the broadband platform. It's the simulation ID for that particular run. I'm just calling that. And then, it creates plots. In this case, it creates plots for all the 3 stations, but I'll pick one of them, which is the first one, the one that we saw, the time series. And this is the result that we got. And we can see those 2 sets together. I guess the blue line is the recorded data. The green line here is the simulations. And remember, the station list had a range of frequencies for which the data was deemed to be good. So those are the 2 lines that we see here. As I said, those are really for informational use. We choose not to just cut plot, so you can still see what it is there, but you can interpret that as differently because of the instruments are have different frequency ranges. Great. So up to now we have one station, right? We're just using this 2001 SCE station, and that's all we've seen. But we can also aggregate the information from all stations. And in this case, I'm going to switch. I think so far we've been using 3 stations. Now I'm going to switch to the full station list, right? You can actually create a goodness of fit plot with only 3, but the results will not look good. The statistics really need more stations and more data points. So for this case, I'm going to import this PSA Gov module from the statistics package. And I'm going to set up the cutoff to 120 kilometers. So when we do this statistics, we can exclude stations that are far away, for example. So 120 kilometers will basically pick up all our stations. And yeah, we want all of those. So we're going to run this module and generate residuals comparing the 2 data sets. And finally, I would like to plot that. So there's the plot PSA Gov method from the plots package. We're going to set up a title here. Creates a plot, and I'd like to see that plot. Here we go. So if we look at the top of the top plot, right? So here we have this data from all 39 stations, comparing simulated and observed time series across periods that go from 0.01 to 10 seconds. So the solid red line that we see there shows the mean. The narrow band is the 90% confidence interval, and the wide band shows the standard deviation. So the way I learned to interpret this plot is that, for example, for periods between, let's see, here between 1 and 5 seconds, I don't know if you can see my cursor, but between 1 and 5 seconds, the red line is pretty close to 0. So that shows the 2 data sets are very close. When the red line dips below 0, then what that means is that for that particular period, the simulations are over predicting the recorded data. So they're coming stronger than the recorded data says. And if the line goes above 0, that means simulations are under predicting what the recorded ground motions were. So that's sort of like how I interpret this plot. And this is one way to see that, right? if I scroll down a little bit, I have a little section here that says additional goodness of fit plots. And the broadband platform or the GMSV toolkit now allows you to see the different ways, the same data in different ways. So I'm going to run this. It's going to generate several different plots. And I'm going to display some of that. So in this plot is basically the same data, and I'm showing different, I think there are 8 different periods shown here. The first one is empty. Well, that's because there's no station that had data valid for that particular period, so it's empty. So they got dropped out. But the other ones, should have more data. And here we see a comparison across VS30. So on the x-axis, you have VS30, and then where you want, ideally, if they match perfectly, all the dots would be here on the 0 line, right? And this is useful to see if we have any bias against, like sites or the type of soil for a particular site. So that would be useful for that. We can expand that if we go to the next one. And here we see a map. I think I showed this plot on the other presentation, but here we see the same data on a map. So it's helpful to see where if there's any directivity or site conditions that happen to cause any bias. So for example, here on the northeast, you have more like reddish dots. So that could be perhaps something like that. There's some a collection of blue dots here. So maybe you can interpret that differently. So I find that useful for that purpose. And finally, you can also do the same thing, but over distance. And there are 2 plots. One is linear, the other one is log. Just try to see if there are trends, like how, for example, perhaps here you can say that maybe there's like a line here, right? Going, it could be some kind of bias related to the distance. So it helps you interpret your data by having this, different ways to view the same results. Okay, so far it's all me clicking through this, but now you guys can have a go as well. We're going to take a look at seismogram comparison plotting tools, which we kind of play with that a little bit up there. But in this case, I didn't mention this, but our data package that's contained in this container actually includes two sets of calculated seismograms. The one that we've been using so far includes simulations from the broadband, and after the seismograms are produced, they are corrected for each station VS30. So after there's a site response module that corrects the seismograms, either amplifies them or de-amplifies them depending on the site. The velocity model we use was calculated with a VS30 of 500 meters per second. So if your station is at actually 500 meters per second, nothing happens. Your seismogram stays the same. Now, if it's if you have a higher VS, then your seismogram, your time series is going to be de-amplified. And if you have a lower VS and a softer soil, then you should expect an increase, an amplification of your ground motions. So, and that's what we've been using, and that's how it's used on a validation run. But we have a second data set, and this one, it's the same simulation, but I disabled the site module. So every single station we have has been computed to 500 meters per second. And I want to compare those. Ideally, I still want to, what I would like to do is pick a station that has a much lower VS30 and compare the two to see if the amplification is working. And also I can pick a station that has a much higher VS30 to see if it's really de-amplified. So we're going to start looking at the station list for North region. This is the full station list. And when I look here, I'm looking for stations that have, let's say, a station that has a low VS30. And I don't know, I mean, you can pick any one that you like. I picked 2029 has VS30 of 266. That might be one of the lowest ones. I picked that one for my example. And for the high VS, I mean, I picked this one that has 1222. So I chose those. I'm kind of, again, looking for more extreme cases, because if I pick like, the 497 VS30, that's not going to be very different. So to get started here, so you pick those, and to get started, I'm going to import this. and then the location for all these input files. And then I have this box. So this is a template we can use. And it's similar to the one on the top of the notebook. I think we plotted, we generated a similar plot on the top. So if you need inspiration, you can look there. But so I'll give you a few moments to think about this. And then I'll come back and show what I got. Are there any questions?
I'm checking the Slack channel. Fabio, there are a few on how to bring up plots in a Jupyter notebook, but I think we're good related to this tutorial.
Okay. Yeah, I just want to mention that I have this box here that, for comparing with the lower VS30 time series, and then I have another one here for the higher one, so you guys don't have to erase your work for the next one. But it's basically the same thing. Just you have to, think about a different station that you want to use and see what the differences are.
Can I ask, when you put the station name in, is it in quotes? Is it string?
Yes, it is. Yeah, you have to come here and type whatever the station name is. I guess for me, I guess I use that 2029 CAS station, so I'll do something like that. And then you have to, and then you have to create arrays of labels and input files. And the way it works is it kind of matches. So the first label goes to the first input file, and so on. And then you might have to adjust the limits there, just in case you want to focus on a particular part of the time series. That might be helpful as well. But it's interactive, right? So you can go back and click again and run it one more time and plot it again until you're happy with what you get. So Phil, I'm gonna be switching to my slide deck again. I'm gonna show one possible set of answers. Just trying in the interest of time here. Oh, I think that's where we were before. Okay, so I'm back on PowerPoint, and if this feels rushed or if you need more time, you can always reach me later, and we can talk about this. I can answer more questions, but in the interest of time, I'm going to be going on here. So this is one possible way to get those. That's what I did for my own solution. Just like the seismogram plotting examples that we have at the beginning, we need to pick up a station and 2 sets of seismograms, right? So the code can take more than 2, but I think we can maybe do up to 12, actually. But here we have the 2 time series calculated from the broadband platform, one with the site response, one without the site response. So, those are defined here in sim site file and sim no site file. And then I create an array, with those 2 files, and I kind of put labels. I just put site and no site. Because that's that. And then I did change xmin and xmax just to zoom in a little bit. So the default values I think are from 0 to 100. But if we zoom a little bit, maybe we can see better the differences between those. And then I changed the title here just for the station name. We don't have to, but and this is sort of what I got. So the seismogram that was produced at 500 meters per second, which is the no site one, which is the red line, you can see, and then the one corrected to the lower VS got amplified. So that's the red, the black line that goes there. So this is the results that I got for that particular seismogram for that particular station. Similarly, I did the same thing for the other stations. I used this 2012 WON station. I kind of changed the X-min and X-max a little differently here because I zoom more. And this is sort of what I got. Again, the one without the site response, which is calculated at 500 meters per second, is the red line. And then once we go to 1222 meters per second, you can see the site response sort of de-amplifying the waveforms to make them less. That's sort of what I got. So it's represented the harder soil that we have for rock. So now,
Fabio, can I make
yeah.
a comment? So I work along with this, and what error I came up with was issue OS not found. Excuse me.
Oh, I think
OS not found.
Mhm.
So yeah, it just points out that to get to run it, you need to run the preceding cells.
Oh, that's right. Yeah, we assumed that you started from the top type of thing. So I just want to mention then, talk a little bit about the next steps for the GMSV toolkit. As I mentioned, this is a new software package for SCEC. We only really began development on this at the end of last year, which was 2022. So we're happy where this is going. Lots of codes are migrated already. The original goal was to use the existing codes, make the fewest changes as we could, and I think we mostly followed that. So there's new code development, mostly adding the command line interface that was not there. So that's all new code to each of those modules. All the tests, small changes in the interface to make sure that we remove dependencies, or sometimes we have to write wrapping functions that for the broadband to still use this, but we have a different way to use that. So what remains now before we can cut a release is finalizing the codes we would like to include. There are a few listed here, like the RZZ metrics, the 2016 Ashfari and Stewart, the ratio and GMPE. So those are some. A few codes from the TS process for time series processing. There's also like to see those there. And a big chunk left is documentation, documenting the command line API, the Python API interfaces, adding lots of examples. I think that's key. More notebooks for demoing how to use the different pipelines and workflows that could be available. So I think that's, including more notebooks would be good. And most of this will make to the GitHub wiki. And we also plan to, document the classes and methods and automate the API so that we can cover most of what we want. So as for a time frame, having a beta version of these codes available sometime next month would be feasible. But a full release with the complete documentation done by the end of, sometime later this summer, at least sort of that's the plan. So with that, I conclude the talk today. I'd like to thank you all for your participation. I added a few links here to the various GitHub repos that we have, containing some of those codes. I truly hope you found this useful, and you can send us questions and comments, to software@scec.org. That's a great way to reach us. So I think that's what I have, Phil. Any questions, please?
Thank you, Fabio. Very nice. Comments or questions before we break? Okay, I'm going to check one more time in the Slack. Looks like we're up to date on the Slack questions. So let's move to our lunch break. The plan now is to, yes, Fabio, thank you. Very nice presentation. Appreciate you putting that together. And the materials are going to be available for people to access going forward. So let's see, right now, our next, so we're gonna go on break here. So we've had our morning sessions. We just completed our morning sessions. we'll go on break until 12:45 p.m. Pacific time. Then we'll start our kind of technology installation, Docker installation, and at 1 we'll begin a session on SCEC community model data access. So I want to thank all people for joining, and please, we welcome you to our next session that'll start at 1 p.m.